Alrighty, let's see what we got here on a lovely Thanksgiving dinner or evening. Maximum number of K-divisible components. So I've previously done this hard. There's an undirected tree with n nodes labeled from 0 to n minus 1. You're given an integer n and 2D integer array edges of length n minus 1, where edges of I is a, comma b indicates that there's an edge between nodes a and b. You're given a zero index integer array of values of length n, where values I is the value associated with the ith node and an integer k. Okay, probably like a weighted graph. Each node in the graph has a certain weight. The valid split of the tree is obtained by removing any set of edges, possibly empty, from the tree such that the resulting components all have values that are divisible by k, where k is the value of the connected component, where the value of connected component is the sum of the values of its nodes. Connected components is like an island of nodes that are all connected that can be separated from other islands. Return the maximum number of components in any valid split. The maximum number of components. Oh. Okay, so k is 6 here. So the maximum number of components where the sum of the values and the sum of the stuff is divisible by 6. Valid split of the tree is removing any edges possibly empty from the tree such that the resulting components all have the values divisible by k. This doesn't seem like it'd be divisible by 6. Remove the edges. Oh, it's not showing up the values, it's showing the node number. I see. So node 1 has value 1, node 3 has value node 1 has value 8, node 3, yeah, okay, there's a 0 node. Node 3 has value 4, so that's 12 total there. And the other ones are adding 1, 1, 4, so that's 6. Okay. Okay. Maximum number of connected components. Is always guaranteed to be in any valid split. Valid split is obtained by removing any edges possibly empty from the series such that the component such that the resulting components all have values that are divisible. Okay, maybe it's something where the sum of all values are divisible by k. Yeah, okay, so it's guaranteed to have a split. Starting with the connected tree. Oh boy. How would I solve this? So how would I traverse the tree in a orderly way? This vaguely seems familiar. I wonder if this is one of the ones where like I'd spend weeks thinking about it. Doesn't seem like I'd be able to solve this immediately. Alright, anyways, I think you start with the edges, the leaf nodes, sorry. You start with the leaf nodes and you would combine, and if it's divisible by k, then obviously you could make that into its own tree, or own island connected component, and that would satisfy a split. So the question is, if the leaf node is not divisible by k, and then it goes like it goes to the next level. First you start off with all the leaf nodes. Remove the leaf nodes that are divisible by k. Then that might cause some connected parent to be a leaf node. And then you remove that parent if it's also divisible by k, maybe? Actually, yeah, if the parent's a leaf node, it's divisible by k, then you should definitely remove. So, would you ever get to a point where you could get to a point where the leaf nodes are all not divisible by k. Let's say, for instance, k is 3. And then let's say I build something that is not divisible by 3. In this case, say k is 5 or 4. And I have a tree that is, say it's pretty simple. Say it's 3, 2, 2, 1. So in theory here, you couldn't really divide this further. If it was something like 3, 1, 2, 2, then you should be able to go up. We go upwards. So, is it like you consider a node? 3, 1, 2, 2. What if it was more complicated though? Let's say it's 3, 1, and then there's a connection here to, let's say, a 3, 3, 3. That adds up to 9. 3. So in theory, you'd break the 3, 1 as the separate from the 2, 2, separate from the 3, 3, 3, 3, 3. Is there any other? I don't think there's any other ways of doing that. Is it possible that is it possible when you see the 3, 1 that it's incorrect to split it off? I think so, because then maybe it's something like 3, 1, maybe something like this. Because once you split off the 3, 1, then the 2's can't be, the 2's can't work by themselves. Maybe you can split off the 3, 1 if whatever sum of values 2 is on this side is divisible by 4, and whatever sum of values that this 2 is connected to on this side is divisible by 4 as well. In theory that should work. There's no reason why it wouldn't work. But then how would you how would you make that determination of the sum of values from here on? I guess you could keep track of the sum of values up to a certain node. Then the trees themselves, the tree itself is not necessarily ordered. Three, one, two. Yeah, it feels like I might have done this. It feels like it was very complicated. If you keep track of for every node, the sum of the values. 3, 1, 2. It'd be something like 4, 4, 4, 4, 2. This could be something like 4, 4, 4, 4, 4, 4, 2. Three, one. 3, 1. Somehow you need to know that on this side of 3, 1 to this thing is summing to something divisible by 4. What is the best way to traverse this? I mean, it feels like it should be... Feels like it should be traversable using going from the leaf to the inner nodes. Leaf to inner nodes. And if you go from leaf to inner nodes, keeping track of the sum of the values of that progress. So what if you pushed the value of the leaf node to the parent node? Is it possible to have multiple parents? Possible to have multiple parents. So, say my leaf nodes are 3, 3, 3. And they're all connected to let's say these guys, both these connect to a 1, and this one is connected to 9, 10, so it's connected to a 2. So 3 pushes its value to the 1, but this 3 pushes its value to the 1, so this makes it a 7. 7, 2, 3. And so this 3 pushes this value to 2, so it's like 7, 5. And 7, 5 makes it impossible, so when you do a push, might be something. So I do a push here, this is 3, 1, so this makes it 4, which in theory makes it divisible. Then how would it make sense to push here? Since there's multiple connections here. Yeah, at this point this isn't actually a leaf node. So maybe I just push the values up a chain. Okay, all the leaf nodes, I push the value. If it's not already divisible, okay, push the value up to its parent. The parent changes to be the sum of all its value and all its leaf nodes. And then the parent checks again if it's divisible, okay. If it is, then it detaches itself. The parent checks that it is a leaf node first. And if it is, at this point it is, so then it detaches itself. I think that's right. Hard to always say. I'll clarify. I think that is correct given my level of self-assessment as to what's wrong with it. So let's go ahead and try to do that. So this is remove all leaf nodes that are divisible by k. That's gonna be +1 to the answer. Push remaining leaf nodes, push their value or increase the value of the parents. Repeat process, and then check again. Each time it does that, there should be some more leaf nodes. Okay, so building the graph. Graph needs to identify where the leaf nodes are. Okay, so I think for most graphs I will use a default dictionary, although this one maybe can use a matrix somehow. I'll figure that out later. Default dictionary of list. This is the key is node, value is the list of connected nodes to it. So for every A, B, and edges, if actually I'll just say graph of A, append B, graph B, append A, and again I'll maybe make a matrix for this. It needs improvement speed wise. Okay, and then I need to go onto the leaf nodes. So I think that just means for every node in the graph, if the length of the list that the node is connected to, or the neighbors, is equal to 1, then leaves dot append this node. Okay. And then I just do the iterative process of changing values of nodes and checking to see. So answer 0 for every leaf node in leaves. I think I need to do maybe a marked. I'm gonna do the marked. I need to somehow track stuff that I've removed. Well, so let's go ahead and just write. So first off, the basic stuff. If this leaf node has a value that's divisible by k, so values of this leaf mod k is equal to 0, then I'm going to remove it. So I think I can say something like, and there's going to be a new leaf set, or the next leaf set. Maybe it's a list right now. I want to remove this leaf from the neighboring connected cells, connected nodes. So actually I think I might want this to be default dictionary of a set, because then I can remove it mostly. So this should be add B, add A, and this is okay. The list of the leaf nodes is still fine. And then I'm going to go through remove leaf as it is a valid connected component. So I think I need to go for every neighbor in the graph of this node. The graph of the neighbor is going to remove this current node, so detach it. And I think maybe at this point I can check to see if this is now considered a leaf. Next leaves dot append this neighbor. No, if the graph of the neighbor is equal to 1, the length of the graph of the neighbor is equal to 1. No, whoops. Length of the graph of the neighbor is equal to, yeah, I think it's 1. It could in theory be equal to 0 if it's like the center node of all leaves connected around it. So I think it should be 1 here. There's some edge cases that I need to work out. If length of graph is equal to 1, then add this to the next set of leaves to be processed. And answer increments. Yeah. And then otherwise this is going to push its value to its neighbor. So yeah, else I guess it's always removing itself from its neighbor, right? Interesting. It's always removing itself to its neighbor. Okay, values is pretty big. Values 10 to the 9th. 10 to the 4th. Trying to figure out when I need to do mod. Maybe I always do the push, and if the island itself is this way K, then just increment 1. Maybe it always does the push, pushing the value upwards. The leaf node should only have one neighbor, right? Actually. Okay, actually, yeah, the leaf node only has one neighbor. So this shouldn't be a for loop. Or if it's looping over multiple things, then it's not a leaf. Okay, so this should be just an if statement, maybe. Okay. For every leaf and leaves. Actually, this is gonna not work, right? So this needs to be out of this loop, so it should be like a while true loop, maybe. Or while there exists leaves. Yeah, something like that. For every leaf and leaves, if values of this leaf mod k equals 0, answer increments, else leaf pushes itself to its neighbor. So it's actually a set, right? Set graph of this leaf is going to be a set. I think I just use 0. Can I? Maybe I have to use pop. Single element on the set. I think I might need to use pop. No, pop doesn't work. No, pop doesn't work. For a single element set, for certain the sets containing a single element, you can use tuple unpacking. An arbitrary element from the set. I don't want to convert to a list. It's stupid. If I know that there's only one element in the set, U equals next iterative of S. What does this mean? Jesus Christ. From iteration utilities import first of this. Yeah, I don't want to do that. Pop add add is red line. Set unpacking. Loop is quite slow. Oh, loops okay. Interesting. Iterate next. That's okay. Maybe I should do the set unpacking. Where's the set unpacking thing here? Okay, element, comma, element, commas, blank, parentheses around that. Okay, so it should be something like neighbor is the only element of this graph for this leaf. Okay, so that case, what I want to do here, I want to remove, no, I want to just push the value. So I think it should be values of neighbor increments by the value of the leaf. So push like 3 up to become a 4 on the next node, on the parent node, and then push the 3 to become a 4. Then I want to remove, regardless, I want to remove this thing from the tree. So I want to remove the thing from the tree next. Maybe I should just start this on the outside. Okay, so the neighbors is obtained. I definitely want to do the removal. So graph the neighbor dot remove this node, and then if graph the neighbor, if the length of graph the neighbor now is only 1, then the next leaves should append this neighbor. That's right. Okay, I guess, okay, this should fail if there's a single leaf, right? If there's a single leaf, then there's no neighbor actually here. Yeah, so if you have a single leaf, well, if you have a single leaf, then actually you don't get here. So if the starting point is a single node, then that node has nothing attached to it. But then if you have, like, let's say you have two nodes, those nodes are both considered leaves, and then let's say both nodes are 4, the k is 4, so both nodes are part of the initial leaf set. First node gets processed, it removes itself. What happened? Yeah, I don't think this works quite yet. It moves itself. Maybe I need to do a processed set. Otherwise there's going to be some sort of race condition as to when things get processed. Maybe, yeah, maybe it should be something like processed as a set. And then if the leaf is already processed, then skip it. Every leaf and leaves. How would it already be processed? Yes, it's possible, yes. If leaf and processed, continue. Was processed to add this leaf. It works, I think, for the two leaf set. Like, I think that works if it's something like trivial, but not trivial, like 4-4. Both things get added to the leaf set. And then one gets processed. Neighbor. One gets processed. Looks at its neighbor, removes itself. Removes itself. The neighbor now actually has 0 neighbors. So it doesn't actually put that neighbor into the next leaves. The other node gets processed. Removes itself from its other neighbor and its original neighbor. I guess maybe it doesn't actually need it. Okay, what if it was like, what if it was something like 1, 2, 1. So both ones are part of the original leaf set. Ones get processed. Makes the 2 into a 4. And the 4 has one connection, then adds that neighbor to the next leaves. Maybe I actually don't need the processed. Okay. So the other edge case is going to be when it's just a single number. Like that's the only node. At that point, well, how many nodes? There could be one node. Okay. So at that point, I guess I could just make an edge case for that. If if n is equal to 1, return 1, I guess. No, the answer should start with 1 within 0. So I'm going to make a new attachment each time. But there's originally 1. Okay, I think this was just Leetcode. So for every leaf, get the neighbor leaf. If the leaf is divisible by k, then remove it. Otherwise, push its value to its parent. Remove itself. The parent is now a leaf. Add that to the next layer. Oh, last but not least, this is why I generally try to do this as the first thing. I need to actually make leaves come next leaves, and then return answer. Remove node. The graph of neighbor, remove this node. Alright, let's go ahead and just see what the graph is. And then maybe here. Node 0 is connected to node 2. Node 2 is connected to 1 and 4, and 0. 1 is connected to 2, 3. 3 is connected to 1. Okay. Seems like the graph is okay. And go ahead and just see that it's getting the original leaves correct. So it should be 0, 3, 4, 0, 3, 4, and 6, 5, 4, 3. Okay. So that seems fine. So what is it trying to remove? It's crashing it. Removing 4 from 1. Seems like it should work. 1 has 4. Remove this node. Oh, fuck me. Seal this leaf. Okay. Not enough values to unpack. Expected 1 got 0. Okay, yeah, that's what I was somewhat concerned about. I guess I can do something like if the leaf itself is only one thing, if length of this graph of this leaf is, I mean, that should be down to like the final thing. Whatever. If length of the graph of this leaf is equal to 0, then I guess I could probably break. Seems like there should be a better way of handling that. It doesn't require me to do that check every single time. Alright. Solved, even if that was very inefficient. Okay, so we need to do created graph, moving nodes from length from set to the neighbors, creating the next leaf, So it's a matter of traversal. Yeah. Could be a matter of traversal. So I maybe could use a queue rather than hmm, could use a queue. So the queue originally has the leaf nodes and process through the leaf nodes, and if the neighbor is not reprocessed, no, I mean it has to remove itself from its neighbors. I mean in theory maybe I can, rather than have a list of neighbors, no, I should have a list of neighbors, huh? I was thinking of keeping track of the count of the neighbors. Then I need to actually know what the neighbors are in order to decrement the count of its neighbors. So it's neighbor for each node. Huh. I'm actually not sure why this is so slow. How do I move along? Keep forgetting my shortcuts. Is it Control? Oh yeah, it's Control X. Oh, I have a print call. Oh, that definitely slowed it down. Okay, slows it down somewhat. Still kind of slow. Sets. Please. Relief. Relief. List. Node and graph. Length of the graph is 1. Answer is 1. Next leaves relief. I wonder if I can say if the length of the leaves is 1, then break. Because if the length of leaf is just 1, then it has to be the last leaf. So maybe while leaves is greater than 1. And then I don't have this check here. I wonder if that works. Oh, oops, that should be length of the leaves. Yeah, so that doesn't work. Oh, okay. While leaves is, yep. every leaf. Check again to make sure that the leaf is not completely isolated. So I don't see how it can be completely isolated if there's more than one leaf, to be honest. Yeah, I don't know how that logic still failed. Well, its single neighbor single neighbor from set. If its current leaf is divisible by k, that's recommends. Push the value. Otherwise, remove this leaf from the neighbor. The length of the neighbor is 1. The user comes next phase. Yeah, okay, I don't know. I don't know why this is slow. Seems pretty fast. Alright, let's do... I didn't really change anything. Can I do a matrix here? A matrix rather than a graph of sets. Can't see how a matrix would be any. The issue with the matrix is the removal of the neighbor. Removal of the current leaf from its neighboring thing. Kind of wanted to have a set in order for it to work quickly. The matrix could remove a particular connection, but then how would you count how would you keep track of the other neighbors or get the count quickly? Values. Yeah, I don't know. This is tricky. When did I solve this previously? December last year. Looks like I solved it. It also gave a very slow answer. Okay, well. It is what it is. Guess this is an improvement over my previous answer on this. Right. So, summary here. Guess I should be thankful that I actually solved a hard problem. So, repetitive process to counting the number of valid islands. Check for valid leaves, value divisible by k, and remove them from consideration. Any leaves that are not divisible, any leaves whose value is not divisible by k kind of pushes their value to their single neighboring parent leaf. Repeat process. Check again for check again with leaves. Actually, remove connection and see if parent. Move leaf from tree and see and add parent to the next set of leaves. Parent has only one connection remaining. So, as an example, this process would be, let's say you have 4, let's say K is 4, and the leaf is, and the tree is something like 4, 1, 2, 1, 2, 5. This 2 is connected with another 8. So 4, 8, and 5, like this 2 is connected to this 8. Like that. So 4, 5, and 8 are all leaves. Initial leaves would be 4, 5, 8. This is the values of the nodes within the node indices or node label. So 4 and 8 are removed. 5 gets 5 pushes its value. So at that point, the tree becomes 1 and 7. So then initial, and then the next set of leaves would be 1, 7, and then basically that combines to a single 8, which is kind of like the last thing. Answer is initially 1 to indicate that the final thing has 1 working component. Okay, then here use a default dictionary or construct the graph with a default dictionary of sets. That's this thing here. And then check find initial leaf set by looking at which nodes in graph are only connected to one element. Iterate over or do the main code in a loop while there are leaves in the leaf set. Iterate over each leaf, process it while keeping track of the next set of leaves. Place leaf sets with each other. Replace leaf set with next set after a loop, and then return the answer. Right. So while there's leaves to be processed, keep track of the next set of leaves. For every leaf to be in the current leaf set. If it has 0 somehow, which is possible, that's kind of an end case to stop. Otherwise, skip the single neighbor for the leaf. Do the logic. Remove itself from this neighbor, and if the neighbor is now only 1 neighboring as well, it becomes the next leaf. time complexity is the O of n plus n, where n is number of edges. Well, then it's just O of n because it matches, right? O of n, where n is the number of leaves. Since each leaf is each node is processed once while in the main loop. Like there's only one time when each node is considered a leaf most. And then space complexity is going to be O of n. Actually, this might be O of mn. O of mn for the graph of default dictionary sets, I believe. I think so.